Oh, I need to do it. What happened? Everything okay? Okay. So part 3 was inspection modes, and as I said, any probe, whether it's an array probe or whether it's differential, plus point, whatever, the first thing we do, oh, tea is getting cold. Single frequency. So you have a single sinusoidal excitation. The magnitude and phase change of the impedance is used as a signal. Then we can, the other mode is multi-frequency. So you can excite a coil at more than one frequency by either by time multiplexing or by a single sinusoid. You know, we have two, you can combine more frequencies in the excitation signal, and at the output you can filter out different bands and get the signals. And there is a reason why multi-frequency is used, you know, and that is when you saw that if the defect is at the support structure, you get a combination. Even for the other one, you asked how do I know what kind of defect it is. So the first thing they do, they know where the supports are located. So they know that this particular signal has both support. So they can suppress the support signal. Okay, so for that, they do two frequencies. Okay, at a very low frequency, the support contribution will be a lot more because support is on the outside. At very high frequency, the support contribution is less, okay, because of the frequency and skin depth. So once you have they have these two different frequencies, they do a combination. They rotate and scale one of the frequencies, and then they subtract the two. The scaling parameters are all predetermined only to make this support signature look the same. So basically, let me try to explain. You have a support structure only, no defect. You take two frequency signals and they look different, but you can simply apply some kind of a transformation, a fine transformation to one frequency signal so that it looks exactly like the low frequency signal, for example. So and then you subtract out and you get a residual, small residual. So if there is a defect, the transformation parameters are tuned to the support signal. So, and when they subtract it out, the support signal will go off, but the defects will be left. And then you know that there is a defect. So that's what they use for multi-frequency inspection. Then you have pulse eddy current. Pulse eddy current is when you excite it with a pulse. Okay, so that means the pulse, if you look at the Fourier spectrum of a pulse, it's got a much larger bandwidth. So it's one way of exciting at multiple, a large set of frequencies, and looking at it as a time domain. It's a pulse, so it's not a continuous excitation. So once the pulse is stopped, then you look at the response signal, okay, and that is a time signal, and we look at that. And then there is also something called remote field eddy current inspection and nonlinear eddy current inspection. Nonlinear is used for ferromagnetic materials. So I think this is one of the multi-frequency. I don't know whether you can see it. You can see the multi-frequency signals on the scope. Anyway. No, it's the eddy scope. It's called the eddy scope. Yeah. Yeah, I think I already talked about all these things. So we talked about single frequency excitation. So multi-frequency excitation is
Pulse.
no, it's two sinusoids at different frequencies. You can time multiplex and excite it at two different time intervals and look at the signals. Or you can combine the two frequencies into a single excitation signal. And then at the outside, at the other end, the received signal have to be filtered out, the different bands, and look at the response due to frequency F1 or F2. So there is nothing much here. Okay. So the advantages, I think we already went over. You're getting more information, right? When you have multi-frequency, you have defects at different depths, you have more information. So you can also, one of the information is how does a signal change with frequency? So you do say frequency F1, F2, F3, F4. The way it changes is indicative of the type of defect, whether it's a shallow or deep defect and all those things. Allows mixing of frequencies to eliminate, say, the support plates signal. So that's one thing. So basically, more frequencies mean more information and so on. So here is, I think, one of the screen of the multi-frequency instrument. So you can get, it's a big, I don't want to get into that. This is just a picture screenshot. Okay, so what, yeah, I think this is what I talked about. What is the application of multi-frequency? Useful for eliminating unwanted indication, application of support plate suppression in steam generator tubes. So you can suppress out this, is called mixing, and the thing is, this is a commonly used method. Most of the eddy current instruments have a button for mixing, and you give them which two frequencies, it will automatically do that. It will remove this will go these two lobes, and all you have left is the defect signal. Okay, so that's one about multi-frequency, and then you have pulsed eddy current. So the driving the probe coil with a number of pulses. So the pulses means you have a broad. Why is it echoing? Can you hear some echo? Hmm. Okay. 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 Ah, much better. So you now have a broad frequency spectrum by using just one pulse, but it's a time domain signal now. So that means that you have a true diffusion phenomena. So the governing equation has both the d by dt of the field and so flaws that are close to the surface will appear first, and if it's buried down, you will get a later signal in the time domain signal. So it has its own use, but it's very slow, and it is used for layered. In the beginning, they used it for layered structures, so that you can then find out whether in which layer the defect is and all that. Yeah, it's application of multi-layer aircraft structure, and also for hidden corrosion and cracking. And this is basically the setup that is used for square wave signal generator, and then you have a time domain signal that you see over here. Okay. Let me look at show you this. A typical signal looks like this. Okay. So we look at what we have there. So this is it's a transient phenomena. So it's a transient signal, and what you have here, I think the curve 1 is a 2-layer. Yeah. Right. Then you have a 40% top layer thinning, and the third one is 0.57 millimeter liftoff. I don't know. It's not very systematic. So these are again for different types of, whether the top of second layer, bottom of first layer, wherever the defect is, you have different signals. So what people do is, once you have the signal, there are features like where does the zero crossing of the signal occur, what's the peak value. They basically look at different features and determine, do the analysis of that. So it's, although we say it's a broad spectrum, because of skin depth, the very high frequency components die out very quickly. So it's only some. And this is an example. They are using a pulse eddy current detection of corrosion in the, in the second layer. And so from the signal, they just looked at the amplitude, peak amplitude at each location. At each location, you put a pulse and get a signal and collect. It's like a C-scan image in ultrasound. And this is, you look at where the zero crossing occurs. So at each point, you look at an image of that C-scan image formed from that. So that is one. And this is again using pulse eddy current mode signal, and you have a linear cross section. So you're basically taking a line scan across a C-scan image, and you get. Okay, so at each, the x-axis is a probe position. At each point, you have a different time domain signal. Very much like a B-scan in ultrasound. At each point, you have a time signal that you collect them all together to get a. So that was a pulse eddy current is one. And then you have a remote field. This is another method. This was, proposed by Tom Smith, I think, from Kingston in Canada. And basically, it's meant for very, very low frequency. They use like, 20 hertz excitation. So what happens at 20 hertz excitation? There's full penetration. And it was originally introduced for pipeline inspection, because you want to know, you want to scan the entire wall thickness. So the nice thing is it's sensitive to both ID and OD. And how does that happen? In the vicinity of the excitation coil, you're basically getting more information about ID defects, because the flux goes into the pipe and then, it turns around and you get the information. So if I have a pickup coil right here, I'll get information about ID defects. If you go further apart, you are looking at flux plot that go to the outer wall and then comes back. So away from the excitation coil, if you put a pickup sensor here, which is called the remote field, you will get information, more information about the OD defect. So that was what they discovered. So if you have, basically you're saying, I put any coil inside a tube, close to the coil, the flux plots are going, are closing very quickly. So they have information. If I pick up that flux, I'll get information about ID. But if you look at the, the weaker field, but goes up to the outside wall and comes back. If I put a pickup there, I'll get OD defect information. So they actually did that over there. Okay, so this is the near. Pardon? Okay, I'm just trying to see if there's another picture again. Okay, so when you have a coil, okay, if you look at the flux plot of a coil, you have in the immediate vicinity, you are closely linked to the coil. But if you look at the, there are also weaker flux going outside, right? So that flux, so if you consider inside a pipe wall, so close to the, if you put a sensor, pickup sensor close to the exciter, you will get information from the flux that is turning, which only goes up to the ID and turns around, right? Whereas if I put my pickup sensor far away, I'm looking at flux that goes around the tube wall, goes to the OD of the tube wall and comes back. So if there is a defect in the OD, I would get more information about that if I put the pickup sensor far away. The pickup sensor is far away. But yeah, that's all. The remote field is just that. But basically, the reason why they put the pickup field far away is then I can get information about OD defect. OD is outer diameter. ID is inner diameter. Yeah, that's what I mean. So this was actually the direct and indirect field interactions. It shows how there is a point in between where this is direct coupling from the excitation directly. It's coupled, only has ID information. So this part of the remote field zone, the flux has traveled to the outside diameter and come back. So this is called, so they did lot of studies on this thing. And so this was for this first people at the Kingston University in Canada did that for pipe, because originally it was proposed for pipe inspection. But then we had another person who looked at it for flat specimen. So they basically had an exciter here, and they put a nice shield around it, okay? So this is an excitation coil, so that the direct linkage, the link, and this is your receiver. So because of the passive, the shield over here, the excitation field is not picked up. So basically this field travels, goes like this, and then only the remote field is picked up by this. So when you want to detect defects in very thick, Here's what I found. Why does it do this? So when you have this petrol bunk where petrol is stored in this steel tank, so this was used actually for detecting corrosion and those kind of, where you have a really thick piece, but using, and these are steel, so they could actually use eddy current of this kind of a setup for detecting corrosion on the outside, deep inside the steel, the floor of the steel tanks. So that's the advantage of the remote field. And I think here is the signal. Exactly. So that because you're not interested in the near field, because that's not going to have information about the outside diameter. So the corrosion is over here. So only the flux that goes through this part is they want to pick up. Yes, yeah, if you want to put something like this, it will have to be empty. And it does get empty sometime, and then, before that. But some of the problems that they face is that this is typically steel, magnetic. So once you excite it, it'll stick to it. And moving it, that means they're going to remove, switch off the current, move it, take the signals. So this is the probe response that they got with that particular thing, and you can actually see defects can be imaged very nicely. So basically it shows, the simple coil, you can have different coil design and you have different modality of operation. You can get a lot of information. So one more modality is a nonlinear eddy current. And this is something that we developed for an automotive company to look at case hardening in the wheel bearing assembly. In a wheel bearing assembly, they have to harden the surface, the inner surface, so that it has, it's stiffer and harder than the remaining. But the hardening depth has to be is very critical. If it is too hard, it becomes brittle. If it's too small, then it doesn't have the required strength. So the case depth is critical. Too shallow means inadequate protection against wear, and too deep means it becomes too brittle. So what they wanted a probe that will determine the case hardening depth. So what is case hardening? It's a metallurgical procedure that I don't know anything about, but I only know that the permeability of the case hardened part is different from the host material. So the acceptable profile, case profile, is something that's given over here. So anyway, so what we defined, so because it is magnetic, what we did do is we looked at a eddy current method, but we used the nonlinear portion. In conventional eddy current, what you have is your excitation signal is very small amplitude. So we call that linear eddy current. So if the red signal is the excitation, the green signal, it's a linear system, so it will be the same frequency, but different phase and amplitude. That's my received signal, the response signal. But in a nonlinear eddy current, we are looking at a very high amplitude excitation. Basically, you're operating in the nonlinear region. So if my excitation signal is of much higher amplitude here, my received signal, because it's a nonlinear method, you'll have some harmonics. So the received signal looks like this. And we take features from the harmonics and determine the case hardening depth. Okay, so that's what we did. So that's the nonlinear eddy current. So yeah, the excitation is always in a single frequency. The only thing we are doing in nonlinear is increasing the amplitude of your sinusoid, so that we operate in the nonlinear part of the hysteresis curve. Okay, so the nonlinear method is based on the premise that the characteristics of the case hardened is different. Yeah. We are using a single frequency. Right. 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 See, all those that I talked about so far, we are operating in the linear region. The power is a very low amplitude signal. So we know exactly for a low amplitude signal, when you're operating in linear excitation, linear mode, there is the relation between excitation and received signal is the same frequency, except amplitude and phase is different. That's all, like a linear system. Okay, because there is no magnetic material over there, everything is fine. But when you have a magnetic material, that has the hysteresis, right? So when you apply, if I applied to the same material just a very small amplitude, I will not get this kind of response. But when I apply a large amplitude signal, that means I'm exciting it in the nonlinear portion of the hysteresis curve. When you have a nonlinear system, the input frequency and the output frequency will have harmonics of the input frequency. Yeah. Magnetic, yeah. Um, it is actually, that's right. So the case hardened section, what we have is access to this side end. The case hardened side is on the outside part, right? Right. So all we are going to do is see if it is, what is the parameter L over here, and the depth, core depth and core length is all. We're just only looking at, it's more like a classification whether, so they gave us a bunch of calibration samples with different values of L and D. So we put our eddy current in a nonlinear eddy current probe, and we looked at what we get. 5 mm, yep, 1.25 mm, yeah. We don't scan the entire range. We are only, once we get a signal like this, okay, let me go to this thing. At one point, we get a signal like this, right? So it's a data-driven thing. So based on the harmonic features, we come up with, using a lot of calibration samples, depending on the harmonic content in this, I know what the defect depth is. So this is at each depth I can do, along the length, I can determine that. Yeah, but you know, the mu itself of the case hardened mu is different from the mu of the steel. Okay, that's all we know. So it looks like, so we know, if you look at it, you can look at it as a layered media. Okay, and whereas the case hardened depth is changing, the thickness of this is changing. Total thickness is there. So the relative thickness of this and this part is different. So that's going to produce one signal. Okay. It's, yeah. That's all. So if you look at this thing over here, so based on the premise that the magnetic characteristics of the case hardened and the steel is different, you will get some signal. We don't know at this point. I mean, and we're not looking at a physics-based method of relating the harmonics. We're just looking data-driven. Okay. Okay, so advantages, the excitation is done at multiple frequencies and spatial locations. Yeah, so we can also conduct the same thing and also at multiple frequencies. So multi-frequency, okay. Okay, so this is basically the method that we used. So this is what the impedance plane plot looks for this thing. Okay, so basically, yeah, you can always do it at other multiple frequencies also. Yeah, we investigate everything, but I don't have the full. We have a full paper on this thing, and that will give all the details. This is a couple of years ago, so I've forgotten the details now. Okay, anyway, but underlying physics is just nonlinear means your signal is going to have more frequency than what you input. Output frequencies is different. Okay, so those are the different modalities of operation. So the last part of this is the inverse problem. So we have looked at the coil configuration, the different modality, and we get a signal. Again, going back to this, how do we invert the signal and get the full profile of the defect? That's what you're interested in. And again, the procedures are very similar, except that now the model is an eddy current model. Okay, so we have any inverse. So this is different. So we want from the transducer response the defect size, shape, location, and material property. So again, we can either classify or characterize. There are some in the bearing cladding depth. They just want to classify it as whether is it inside the range or outside the range, and for the L and for D. You're not really looking for how, which it can be done too if you do it in a much, we look at it at each point in space, we should be able to do it. And the other approach is the iterative approach of using the direct approach is the inverse model. This is the neural network based approach, totally data driven. You have data, simulation data for different defect profiles, train it and get it. Otherwise, you do this iterative approach, and in which you can get, so you can parameterize your defect profile in terms of depth at each location and do that. Okay, so this is the, okay. So these are some examples of eddy current defect characterization. So this is the true profile, and we were able to get these things over here and so on. Fairly good. The other thing we also did in the case of eddy current, we did a lot of work on what we call system based, which is basically neural network based, but to get the defect profile. And this we showed for the for the nuclear power plant defects in the tube wall. Okay, I'm not going to go through that neural network. So basically, we looked at multi-frequencies, eddy current signal, got a lot of features, how the frequency trend at different frequencies, the amplitude, the peak amplitude, the phase, and all that. And we trained the neural network. Okay, this is the training part. And then once it is trained, we put a test signal. So So what happens, you put a full C-scan image and it takes scan by scan, and at each point it estimates the depth, and it comes out, we get a result that looks like this. The nice thing is, the other thing we also did in order to train it better, we said, okay, we'll take 3 scans, take the features, and predict the depth at the middle point. So it's just a little small modification, but the important thing is that it gave us excellent result. You know, the current, okay, let me see, which is the true defect profile is this magenta one, the thing, the metallographic thing. That's the blue colored curve. Now, these two is what the industry practice. They have a very conservative, it's more like a calibration type approach, and they have this. And the neural network approach produced something that is very close to with the blue signal. We had 2 different types of neural network, and we're able to get much better. These are actual experimental signals and actual defects from a decommissioned steam generator unit. We were able to pull out the pigs, the tubes, and do a metallographic evaluation. Here's another example. In this particular case, the calibration approach was also pretty good. This is the true profile, the metallographic profile is the blue colored one. And that is one of the neural network. And here's another example. The blue profile is the metallographic defect profile. This is what industry currently produces, and the neural network produces is shown over here. The features are, we take 3 different frequencies, and at each frequency we look at the peak magnitude and the phase at the peak magnitude. Simple thing. Of neural networks is typical 3 layers. We don't go more than it's a simple multi-layer perceptron network. But the thing is, we take 3 scan signals and predict for 1 depth, then the next 3 scans and so on. So that sort of produces quite a accurate thing. So the advantages of eddy current inspection I've listed: sensitive to small surface cracks, other defects, and also near surface defects. He gets the results in real time. Equipment is usually very portable, pretty small. But one thing I think, let's next one. So the limitations are that only conductive materials can be used, and only near surface. Can't go for very deep, very thick samples. You can't use it. I think that one of the big disadvantages, can you just look at the signal and interpret? When an operator is just scanning and producing the signal, it's difficult to interpret those signals looking at that. And sometimes the surface finish, there's a lot of roughness that will produce also a background noise. Okay, so this is basically the summary. So what we have done in this eddy current NDT, physical principles, transformer, analog, the different geometries, different modes of operation, and data analysis. So I don't have anything else. We can just have a discussion, follow. Okay, I think I took out some of, okay. So these are some of this is the older one. It's an analog meter, and this is a digital scope. Looks like this. You can connect it. You can have a little signal screen here, or connect it to a laptop in real time, and look at it over there. And you can print out a strip chart. And this also is an old one. You know, if you go to the new, the latest, equipment. In fact, there is a company in Pune. It's an NDE company, and I'm trying to remember the name of this person. He has, he has a totally digital Ediscope, and the entire PCB is like a credit card size. Of course, if you want to look at the signal, you have to connect that to maybe through a Bluetooth device, go to a computer screen and look at it. So this is also outdated, not updated my slides. But it's very important. You get the the probes. I showed some. Okay, see, the probes look like this, and you can see this thing. He's got a handheld meter, and this is the probe size. You can just scan and look at the signal. Manually running it here. These things. Oh. A differential. Okay, I had one place where you have a Z-Tech coils. Differential coils are typically for the tube geometry. OD probes, okay. These are all just, these big probes are, the bigger the size, the lower the frequency. So, oh, so I've gone to the wrong way. Okay. These actually are differential coils. So some of these, they just look like this because they're all packaged inside. What?
One coil is like this.
Yeah. Yeah. Yeah.
One we are meaning correct. Other one we are
No. See, the coil is wound like, you have the same coil and it is wound in the opposite, moves in the opposite direction. Yeah, both the coils. So both coils are there, single excitation source, and you're measuring this differential impedance. Yeah. 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 So I thought you just wanted to see a picture of a differential coil probe. Okay. So you can also have, in the way back, they used to have a bridge configuration. So you have two coils and two arms of the bridge, and you look for the null signal. Then now they have the differentially wound. Yeah. Yeah, different direction. Yeah.
When we this sample will generate magnetic field. That will be dependent.
Then say it again. When you have one coil, yeah. Right, but the configuration that I'm talking about is for tube geometry. So both of them are are inside a tube. If I have a differential on a flat geometry, it will be totally different. The way it's designed will be different. You're going to have two different things, and you're basically subtracting out. that complete configuration is only the way the differential probe in a tube works. The tubes, yeah. Yep. Otherwise, done. Is there any questions there? Okay, I'll take it out. What? Yeah. If you use low frequencies, it can also go for depth at different depth. But see, ultimately, wherever the defect is, with whichever depth, you are only measuring the surface field. But low frequencies, this surface field will have information about deeper defect. At high frequency, it will have only surface. The field is on the surface, but information could be. So it is actually used even for thicker samples. I thought I had it in this talk, so maybe it's coming in a later talk where we have done something for thick samples. I think the last lecture is where I have time. I'm just trying to see where I thought I had some slides on that. Okay, yeah, this is the plus point geometry that we simulated. You can see this red colored thing is the coils. And these coils are interwound, it's not one and then top of the other. These are sort of meshed in between. And this green thing is actually a core, ferrite core. These are all commercial designs. And so we developed a software that can model all that. And we got very good agreement with the, this is one I'm going to talk about just for the last. This is the system that we developed using GMR and eddy current excitation for scanning of fastener sites. And this is the system that Boeing is using right now for rivet holes. Batteries, right? So it's not connected, my output. So that's, I'll talk about the last day. I thought of talking about a full project, right from conceiving the ideas to simulating, optimizing, designing, instrumenting, and then getting the data and data analysis. No, seldom nothing is manual. If you look at the steam generator. Yeah. But sometimes. Right. That's right. But when they do something manually, they're looking at a small region and they're looking at defect. See, industry analysts, I think they know exactly where they've seen frequently defects appear in a certain part because of local stresses. And it's just a local area that he can scan and determine whether there's defect there. If you want to do the whole sample, and if you do everything manually, definitely you're right that the liftoff is going to vary. So the way it happens in the airlines is they mount the wheel. That was for a wheel, I think, aircraft wheel. It's mounted on it, and it rotates, and then the probe is kept in a place, and you get the signal. That particular thing is just for the photograph. can't, you can do only a local area man. Most of the industrial tubes and everything is all by robotic system, scanning system.
Any commercial entity?
I think they, I've met with BARC has its own NDE group. IG Card has its own NDE group. IIT Madras has a huge NDE group. GE in Bangalore had a own NDE group. IISc, the Aerospace Engineering Department, has a big NDE group. So these are the places where research is going on, but where the all the nuclear installations, I'm sure there is, in the US, there are companies that do just the inspection. There is an outage for a couple of days, and they come and do the inspection. It's them. I don't know how it is done in India. All the nuclear, you have a lot of power plants. I don't know how old these power plants are getting. I'm sure they need some kind of NDA of the heat exchange tubes to be done. But there are and all HAL, NAL, DRDL, they all, in Hyderabad, they have DRDL. So I visited there, and because they have this solid rocket, booster rockets, and they do inspect those things and I visited, and they have that's all done internally. But for nuclear and for aircraft, I don't know whether each airline has its own ND group that does it, or whether it's done by, I don't know. I don't know.
Indian Railways.
Yeah, over the rails. I know. I don't know how exactly it's done. We are doing a big project for the American Railroad, looking at ultrasonics, fiber optics, and eddy current type of thing. But I think most of the time it's they are done internally by all the airlines. We have so many airlines now, and we definitely have to do some ND. Probably it's done internally. Even in the US, I think airlines do their own. It's only the nuclear companies they have ZTEC or Arriva. There are different companies that have contracts for doing inspections. Because companies like ZTEC, they are the ones who produce the probes. They design and build the probes. They have all the information about how the data, what's the data format, how it's stored, which they will never share with anybody. And so they also do the analysis. They have their own analysis software that they do. Many of our algorithms are sitting in their software too, working with them for a long time.